Let's do this.
Okay.
Go team.
So this is 2.9. This is kind of one of those moments that we've been waiting on for a long time. We've been studying exponential functions. Now we've studied, this week we did inverse relations. We talked about functions that undo each other. The day that we did inverse functions, Joseph asked the question, is this like natural log and e? Yes, exactly. That is what this is. So we've been doing exponential functions for a minute. We talked about how we can change an exponential function with a dilation, translation, all of these things. Now, today, we're going to talk about how we can work backwards with an exponential function. Logarithmic functions. Okay? So that's our topic of discussion today. I don't know what's going on back there, but can it... Yes? 7. Okay. All right, so an important concept, it says every operation has exactly one inverse or opposite operation. We learn inverse operations because these will allow us to solve equations involving various operations. So if we're solving, okay, imagine the operation is addition. What would I do to get x by itself here? Subtraction. So the inverse operation for addition is subtraction. You can go ahead and put that in the box.
We're not going to write the inverse operation?
That is to subtract.
No, what do we like the actual minus?
Oh, no. You don't have to solve it. What would be the inverse for multiplication? Oh.
We're so smart.
Okay. And then for cubing, what would be the inverse operation?
Square rooting.
Cube rooting. Okay. So
I'm just going to draw this.
cube root would be the inverse operation. Here's what I always think when I start dealing with roots and powers. I always think that the inverse operation is the reciprocal power. Reciprocal power. So if I have x squared and I want to undo that, I want to raise it to the reciprocal power, which would be 1/2. Are you understanding what I'm saying? If I have x to the 3/4 and I want to get rid of that, I would raise it to the reciprocal power, the 4/3. Okay, so this cubing and cube root business is kind of limiting. This goes all the way through the whole gauntlet of numbers that you could think of. If I want to undo an exponent, I raise it to the reciprocal power and I get rid of it. Okay, that is different here. Look, x is my base versus in this exponentiation, which is a fun word, x would be the power here. So those are two different things. Are you understanding what I'm saying? Okay, so to undo this exponential business, what'd you say? Log it, right? And you guys know this from last year. I talked to a guy last night it was in my Facebook group, and he's saying, how do your kids solve these problems, these exponential problems, if they don't know logarithms? And he and his class, they're kind of pulling their hair out right now, because on all of the ones where you had like 3 to the x is equal to 7, well, to solve for 7, what they're having to do to solve for x in this situation is they're having to go to their graph. And they're plotting y equals 7, and they're plotting y equals 3 to the x, and they're having to find that intersection, which we did. We did a lot of, right? But you guys have such a leg up because you've already been through an Algebra 2 course where you were solving with logarithms, which makes this so much faster, right? I told him my class wants to do logarithms, so we used logarithms to figure out how we wanted to place our window so that we could see that intersection. We're kind of doing it the very hardest way, but that's kind of how we do things. So it's fine. Just know that you guys already have kind of a grasp on this, which is amazing. It's really good for you.
Joseph hates it.
It's fine. What does Joseph not hate? All right, so recently we learned about exponential functions and their properties. We would like to solve equations involving exponential functions, which creates the need of an inverse operation. Enter the logarithm. It says, just as we write rational numbers in decimal form and fraction form, we can also write equations in two different forms. Those two forms are exponential form or logarithmic form. logarithmic form. The A is generally silent if you're in Texas, logarithmic. But if you're anywhere else, you might say logarithmic with a little. These forms are equivalent statements that represent the same claim. We're not changing the problem when we convert back and forth. We're simply rewriting it in a new form. So we see here exponential form would be like b to the a equals c. The way to write that in logarithmic form is to say log base b of c equals a. So a couple of notes here. This was blank on the solutions, but I was glad that he left us a place to write a few things. One thing that I want you to write is the base is the base. The base is the base. The base is the base, okay? You can sing Meghan Trainor. I mean, that was probably a long time ago, but it's fine. I'm old. It's fine. Okay, but it's a base.
Yes.
What's a base?
Okay.
No.
No, it's a base in a problem right here.
Never mind.
Can you tell that the base here is b? And the base on this logarithm is b?
Yes.
So if it's the base, period. In either form. The bottom number that's in the basement is the base on both. Okay? The second thing that I want you to write is the log is the exponent. The log is the exponent. And I taught you this last year. What this means is the logarithmic statement equals the exponent. So why I put is instead of is, you could put equals. So whatever the logarithmic statement is equal to is the exponent in the exponential form. Can you see that? The log is the exponent. So the log is equal to the power. Okay, so now if I go back and I look at this exponential form, I can see the base is the base. So I'm going to have b to the a power, because that would be the exponent, equals what's called the argument. That's this c part. C would be the argument. Okay, and I don't have any help for that. It's just you got to, if you can get the base and the exponent in the right place, then the other numbers obviously. Okay. All right, so it says if the base of a log expression is 10, if the base is 10, this is called the common log, and it's written without a base. So, for example, log of 3 is understood to have a base of 10. So the way that you could write that is to say log base 10 of 3, or you could just call it log 3. Everybody remember that? Yeah. Okay, that's the common logarithm. You read it as log base 10 of 3. Those are the words that you would say here. Log base 10 of 3. All right, so let's go on. So example 1, it says just convert. That's all we want to do here. We want to rewrite it out of exponential form into logarithmic form. Okay, so everybody do number A with me. The base is the base. So this is going to be log base 3 of 9 equals the exponent 2. The log is the exponent. So the log equals the power. Okay. So real quickly, number B, log base 10 of y. So what if I just write log y equals x? Y'all okay here? How about this one? Log base r of w is good. What is this?
Oh, that's natural log. Oh, we don't know that.
Okay, so hold on. We don't know that yet, right? We could call it log base e of y is equal to 3x. Log base e of y is 3x. That's not wrong. We know in this class we've learned last year, if it's log base 10, we don't have to write it. We just write log and then the argument. If it's log base e, we write the natural log. Sure, I'll let you go ahead and make that move.
And can you, would you throw the 3 under the natural log? Turn it to a fraction?
If you were solving for x, but they just want us to rewrite right now.
This would be e to the 4th. Oh my gosh.
Okay, so let's go on to example 2. Now we're going the other way. These are all logarithms, and they want us to rewrite them in exponential form. Okay, remember the base is the base. It equals the power. So I'm going to raise the base to the power. So 7 squared is going to be x. We're not solving here. We're just rewriting. 3 to the x power is equal to y.
10 squared equals
10 squared is y.
e to the 4th equals 6.
E to the 4th equals c. Very good. Okay? So we're just rewriting. We're saying the same thing differently. All right, moving on. Now that we understand how they work, we can evaluate. This time we are actually trying to figure out what's happening here. Okay, so the first thing, it says without a calculator, which is important. The first thing we're doing is we're realizing what it's saying. It's saying 2 to some power of x is equal to 8. What is x?
To the 3rd.
So log base 2 of 8 is 3. Do you see the question that it's asking? 2 to what power makes 8? That would be 3. In this question, 5 to what power makes 25? So what's x? X equals 2.
4,
Okay.
8, and 16. It's 5.
2 to the what power makes 32? It is what?
5
So log base 2 of 32 is 5.
squared. Whoa, that'd be the 1/2.
No. 10 to the x
No,
is 100.
E would be.
Oh, so x is 2. Okay. How about 16 to what power gives me 4? Half power. See, there come those reciprocals that we were talking about earlier. 3 to the what would make me have 1?
0.
Anything to the 0 power is 1. So if ever your argument is 1, the answer is 0. If ever the argument is 1, the answer is 0. Are we good with that? Okay. Log base 10 of 10.
1.
How do you know?
Because 10 to the 1 is 10.
Okay, so this is important. This brings up an identity and something that I want you to have in your toolbox. Anytime I have log base a of a, the answer is 1.
What?
A to what power would give me a?
1.
1. So anytime my base and my argument are the exact same number, the answer is 1. That's crucial. Log base 10 of 10 is 1. Log base 3 of 3 is 1. Log base x of x is 1. Log base a of a is 1.
And this one would
No
be
comment.
-1.
Well, all right, so how did I get 6 to what power would give me 1 over 36?
It'd be -2, not -1.
So how did I get in the basement? Well, my power was negative, and then it got squared. Can y'all see that? So the answer here is, right, because 6 to the -2 makes me put it in the bottom as 6 squared. Okay, so look for that. If you have fractions in your argument, look for your answer to be negative. Okay, here we go. Use a calculator to evaluate the following expressions. Guys, on your calculators, you have to put the base. The base is 10 unless otherwise noted. So I'll give you a few minutes to crank those out. When you have those numbers, check them up here. I'll tell you what I got.
.9542.
Or Truett will tell us what he got.
Oh, okay.
No, that's great, Truett. It's great. You're good. 0.9542.
Yeah.
What else?
3.787.
Look at it says include at least 4 decimal places.
3.7871.
2.5219.
I'm using the little approximately equal signs because I know that there's some rounding here.
Oh no, I'm doing
They're the squiggly equals. Good, good? Questions so far? Okay, moving on. It says one useful purpose for logarithms is when dealing with exponential data. Exponential data can be very challenging to display graphically because the values may start out very small, but they grow really quickly. So before long, we've outrun our graph, right? And also, it's difficult to create a display that effectively shows the smaller value. So if I really get in here and try to see what's happening with the smaller end of my graph, then I lose what's happening up here on the large end of my graph.
Could you start from the right now?
You could start from the right.
No, then they're going to be super
Use a
far
regression.
apart.
You use a regression and just predict it. Just don't even care what the data actually says and just regress. Throw in your calculator. Well, actually what they do is they use logarithms instead because the inverse function shows up a lot better on the graph. I can fit it in the window better. Okay? So this is interesting. I spent a very long time trying to figure out exactly what this was saying. And trying to also figure out, like, how do these two graphs relate? I don't understand what they did here. It's confusing. If you are Berlin and Cambry, this is what I was so upset about. They're in second period the other day. They were in here, and they were like, what is wrong? Oh, this is bad. Okay, so here's what I want you to look at. It says the population of English Americans in the United States since 1620 has grown exponentially. The estimated population is shown below from 1620 to 1820, so over a span of 200 years, where t equals 0 represents the population in year 1620. Are y'all seeing that? Okay. The graph on the left shows the population using a normal scale on the vertical axis. Because the population expanded into the millions, the data points representing the years 1620 to 1700 are almost indistinguishable because they had to show such height here. Then we lost a lot of information down in the first 100 years. Can you see that? We have no way of telling what's actually happening there. The graph on the right instead uses a logarithmic scale. Using a logarithmic scale allows us to view all the data points relative to each other so we can see more in this picture here. But I just had the hardest time seeing that these are the same thing. So here's what I want you to do. We're going to pick a dot, okay? We're going to pick, Ruth says this one. Give me a second. Let's do, I don't know, population 80. This one feels, population in the year, in 80 years after 1620. So when would this be? 1700. Okay, so now let's track that number across. Try to be, as accurate as possible. And I want on your calculator you to type in 10 to the 5.2. 10 to the 5.2 power. And then push enter.
158,489.
Yes.
Did I read that right? I read that right.
Okay? Which is going to be somewhere really small as it relates to a million. Okay? So let's see if we can come up with a number that maybe fits on this graph a little better. 200.
200.
At 200? The one at 200. Okay, well, I drew all the way across on that one. So looks like it ought to be about 7 million, right? So at 200, let's try on this graph.
Well, I got a 3.
It'll be like 10 to the 8.
10.6, 10.68 maybe? 10.66? I mean 10 to the 6.66?
4.5708 E6.
You got 4 something?
Whenever I did to the 7.5, I got a 3 something to the E to the 7.
Try like 10 to the 6.8. The problem is these are growing so fast. Try 10 to the 6.8. That's closer. It's supposed to be right at 7 million. So you got 6 point something million. That's how they're relating. Okay? We're having to really estimate right there. But if you put on your calculator 10 to the whatever, based on the logarithmic scale, you should output the population on the left.
So you only get 10 million if you just do 10 to the 7. Oh, Lord.
Yeah, which is going to be above the 7.
Oh, okay.
You see what I'm saying? Okay, so let's go on to the next page and we'll see more of how this is working. This is the population. It's a picture. It says the population of data of English Americans in the current United States for the years 1840, 1860, and 1880 are given below. They want you to plot these data points on the graph. So in order to convert it between the exponential data that we've been seeing and the logarithmic data that they want us to plot, all you do is log the population. So you're going to have log base 10 of 17,009,069,453. 17,069,453. You're going to do log base 10 of that number.
7.2.
Okay, it gave me 7.23.
Yeah.
So you're going to plot that at, this is year 1840. So we're 220 years after 1620. You're going to go up to 10 to the 7.2. 10 to the 7.2 power. Dots on here are very hard. Does that make sense? Okay. So it's like 10 to the 7th. You're raising it 10 to the 7.23.
Oh yeah, I got the right number, but what year is it? Like when
220. Yeah, because these are years since 1620. All right, so do the next two. At 1860, when I got 7.497.
Yeah.
So that was up a little higher. Yeah, 7.7006. So because we have these absolute perfect points here, let's try to work this backwards, since we have better ideas of what these numbers are than we did on these other ones. Raise 10 to the 7.7006 power. 10 to the 7.7006 power. Right. That's what, see, down here we got 50 million for the output. You see how those numbers are working actually? It's a little easier to see if you have the exact exponent that you would raise it to. But if you do 10 to whatever power this is, you will get the population in that year. Cool? Okay. The last thing we're going to look at here is called what is this called again? Semi-log plot. I forgot. Semi-log plot. Okay, it says one common type of graph with logarithmically scaled vertical axis includes grid lines as shown. Oh, why can I not speak? This type of coordinate grid is likely to appear on the AP Pre-Cal exam. Okay. Okay, so I want you to look at this diagram, look at this graph, think, and then let's see if we can come to an agreement here.
Look at this cool thing the idea is so look at that. It's even got shading and everything.
What?
So what are we looking at?
Well, you're looking at this picture, and we're supposed to plot the following points on the coordinate plane. And I want you to see if you can figure out how to plot the points. Emma's got a clue. Let's see if I can.
Each line is 10.
That looks like an inefficient way to plot anything.
How about that? Emma, is this what you were thinking? Let that be A.
Why is that A?
The whole box of the line is
That point is A.
Why there?
Why there? Okay, let's do another one and see if you can catch it.
I figured it out.
Oh, it's a puzzle. All right, so 2, 300. I'm going to go over to 2
1, 2, 3, 4,
right here.
5, 6,
Oh, that's actually kind of neat.
This is point B.
That's so cool. Okay,
So I went up to 100, and then each one counts by 100, 200, 300, 400, 500. Each point after that counts up by 100. It's scaled differently, right? So each point after 1 counts by 1s. Each vertical line or horizontal line after 10 counts by 10s. Each horizontal line after 10 counts by 100. Okay, so 3, 2, where's that going to be?
It's gonna be down. It's like the second one.
Right here.
Oh, this is our last example.
And then the last one, or D14, 415, so 10. Oh, right here?
Yeah.
Y'all agree?
Maybe halfway between.
Halfway between? Yep. And then the last one, E5, 350. So 100, 200, 300, I think right here.
I have a question. Would C be like one lower because 1 is like the
1, 2. Yeah, I think you're right. I think I missed C. Good question. That feels better. Everybody okay here? The hardest part of this lesson was seeing what was happening with the exponential and the log. How are they going from one graph to the other? Could you see why it was necessary to look at these numbers logarithmically, then exponentially?
Yes.
Why?
Because you can actually go accurate. Well, somewhat accurate.
Not so much the accuracy, but you could see better. You can see exactly where these numbers are falling a little better. All right, that's all for today. I want this assignment done. Let's do a big homework check tomorrow. Those of you that are here, those of you that are not here, we'll homework check first thing on Monday. Deal? No work tomorrow, no lesson, no nothing. We're in here and we're just workaday.
I love the common graph.
Can I go too? Like as soon as